Section 25.6. The transitions among the ground and excited states. Not all electronic transitions are allowed. Selection rules dictate what electronic transitions are allowed, what electronic transitions are forbidden. The photon-induced electronic transition probability is proportional to the squared modulus of its transition dipole moment, mu mn vector. So this transition dipole moment is a vector. Mu denotes dipole moment. M and n are the initial and final electronic states. So now you can tell if this vector has a length of 0, then the transition is forbidden because its transition probability is proportional to 0. When this mu mn is non-zero, then this transition probability is non-zero, the transition is allowed. When this mu mn is large, then the transition probability is large. The transition intensity is large. So again, this is the equation. The electronic transition probability is proportional to the squared modulus of a vector. And this vector has 3 components, x, y, and z components. So this is the x component of the transition dipole moment. The integral of psi sub m star. Star means complex conjugate. And then mu sub x, that's the dipole moment of the molecule in the x direction. And this is the wave function of this nth excited state. This is y component, z component. You just need to replace mu x with mu y and mu z. Over here, this is the transition dipole moment vector. Again, there are 3 components in the x, y, and z directions. The squared modulus of the transition dipole moment is simply the sum of the squared modulus of the x component, the squared y component, the squared z component. So now we can use this equation to determine whether this is 0 or not. If mu x mn, mu y mn, and mu z mn are all 0, okay, when all 3 are 0, then we conclude this transition dipole moment vector is 0, the transition probability is 0, the transition is forbidden. If one of the 3 components, any one, is non-zero, then we have a non-zero vector here. That means the electronic transition is probable. Now let's look at 2 examples. In the hydrogen atom, the 1s to 2s electronic transition is forbidden. The 1s to 2p electronic transition is allowed. So we're going to prove this. Let's look at the 1s to 2s electronic transition, assuming the electron spin is conserved. We'll just look at this x component. When we look at this x component, we need to be sure that this equation should be used. We need to have the initial and final wave functions. All right? You can put initial here or here. It doesn't really matter. And then you put this mu sub x in the middle. And mu sub x is proportional to x. Mu sub x is the partial charge multiplied by this distance between the 2 partial charges in a molecule. In the hydrogen atom, it's easier. This x is simply the distance between the electron and the nucleus in the x direction. In a molecule such as HCl, H has a partial positive charge. Chlorine has a partial negative charge. And this x is the distance between H and Cl. the dipole moment of each cell is simply the partial charge multiplied by the distance between each cell. Now get back to the hydrogen atom. It's a lot easier. The dipole moment of the hydrogen atom is simply the charge of one electron multiplied by the distance between this electron and the nucleus in the x direction for this x component. Now, when we look at this integral, we can easily see the 1s wave function and 2s wave function are both even functions of x. And this x, you can tell, is an odd function of x. So you are integrating an odd function of x. The integral of an odd function is always 0 if its lower limit and upper limit are the opposite to each other. This is because the integral from negative infinity to 0 cancels the integral from 0 to positive infinity. So in this case, this integral is 0. What about this integral? This integral is just 1. Alpha is a normalized spin function. Similarly, you can prove the y component and z component are all 0. Therefore, this transition dipole moment is 0. The transition is forbidden. Now let's look at this 1s to 2p electronic transition. Let's arbitrarily choose 1s to 2px. You can prove 2py, 2pz in a similar manner. So right now, I'm going to just look at this 1s to 2px transition. I will examine the x component. And in this case, if we look at this one, 1s is an even function of x is an odd function of x, 2px is also an odd function of x. So really 1s is e to the power of negative r, and r is an even function of x. This is just x. 2px is x times e to the power of negative r over 2. So overall, the product of 1s, x, and 2px is an even function of x. And this function is always non-negative. So if you integrate this from negative infinity to positive infinity, the integral from negative infinity to 0 do not cancel the integral from 0 to positive infinity. They are the same. They have the same sign. They are both positive. So in this case, the x component of the transition dipole moment is non-zero. And that means the transition dipole moment vector is non-zero. And this is a allowed electronic transition. What if I change this transition to 1s to 2py or 2pz? Same thing. You just need one component, either in the y direction or z direction or x direction, to be non-zero. And then you have a non-zero three-dimensional vector. So when we change this x to y, you need to change this x to y, change this x to y, change this x to y, and then you'll see this time the y component is non-zero, the transition is allowed. Now let's look at this spin flip from alpha to beta. So we learned this from 1s to 2px, this electronic transition is allowed. But over here, we're talking about alpha to alpha transition. The electron spin is conserved, and this integral is simply 1. What if we have this electron with initially alpha spin and finally beta spin? Is this transition allowed or forbidden? Well, this is strictly forbidden because the integral of the complex conjugate of alpha times beta is 0. The integral of the complex conjugate of beta times alpha is also 0. So spin flip is strictly forbidden in an electronic transition. Now let's look at this Yablonsky diagram, which summarizes a lot of different electronic transitions. First, let's look at S, S0, S1, S2, and then look at this T. S means singlet electronic state, T means triplet electronic state with a degeneracy of 3. So S0 is the singlet ground electronic state, first excited singlet electronic state, second excited singlet electronic state. So over here we have the labels, energy levels, black lines, absorption, blue lines, fluorescence, green lines, phosphorescence, red lines, and then we have this internal conversion, vibrational relaxation, intersystem crossing, and those are the time scale of all different transitions, including electronic and vibrational transitions. So for example, this absorption, this means absorption of photon takes place in a very short amount of time. So now let's look at the energy levels of S0, S1, and S2. And this is T1. The T1 energy level is typically slightly lower than S1 due to the exchange energy. Again, if all other conditions are the same, 2 alpha electrons versus 1 alpha and 1 beta. The 2 alpha electrons has lower energy because they have the same spin, therefore they cannot occupy the same spatial orbital. They cannot have the same quantum number for their spatial wave functions. That means 2 alpha electrons can better avoid each other than 1 alpha and 1 beta. And therefore, the T1 electronic state usually has lower repulsion between electrons with the same spin than the S1. So that's why. Now let's look at absorption. So from the S0 to S1 or from S0 to S2. You see 4 arrows here and 4 arrows here. This is because for the same electronic transition, you may go from the ground vibrational energy level to the ground first, second, and third excited vibrational energy level. Same here. Well, again, if you review this from constant vertical excitation, you'll see it's possible to change the vibrational quantum number. So this is absorption. Fluorescence. So the lifetime of the excited state is typically short. So this can just undergo de-excitation back to the S0 electronic state. There are also multiple arrows here because, again, even if you start with a 0 vibrational quantum number, you may end up with 0 or 1 or 2 or 3 vibrational quantum numbers. All right? And I don't know which one has the greatest transition intensity. Again, it depends on the overlap between the vibrational wave functions of the initial and final states. Fluorescence. Fluorescence undergoes the flip of electron spin. So over here you may have 2 alpha electrons. Over here you may have 1 alpha and 1 beta. So you need to flip the spin of electron. That's a violation of the conservation of the spin momentum. So when this happens, usually there's another electron spin flip going on at the same time, just to conserve the angular momentum of electron spin. And that's why this process is extremely slow. It's as slow as 10 seconds. Oh, but if you look at fluorescence, the electron spin is conserved, so it can be really fast, 1 nanosecond. Over here, it can be 1 second or 10 seconds. So that's why fluorescence takes much longer than fluorescence, because it's called spin-forbidden electronic transition. Phosphorescence is spin-forbidden. Fluorescence is spin-allowed. Now let's look at internal conversion. This is internal conversion. you can go from S2 to S1, you can go from S1 to S0 without energy change. So really, this is the ground electronics, the ground vibrational state in the second excited electronic state. So you need to look at a combination of the electronic quantum number and a vibrational quantum number. All right? So both numbers change during this internal conversion. Over here, this is the vibrational excited state. All right? Okay? So 0, 1, 2, 3, 4, 5, 6, 7, 8. The vibrational quantum number is 8. So you can see the vibrational quantum number changes from 0 to 8. The electronic quantum number changes from 2 to 1, from S2 to S1. So both vibrational and electronic energy level change. Same here. Okay, same here. So this is the ground vibrational energy level. This is highly excited vibrational energy level. Right? So you are losing the electronic energy, and you're giving this energy to the vibration of the nuclei. Now, vibrational relaxation. So that's simple. It's just the decrease of the vibrational quantum number. Over here, it's from 8 to 0. Over here, it's from 3 to 0. This vibrational relaxation is simply the transfer of the vibrational energy to the surrounding molecules. Intersystem crossing, this is one example from the S1 excited state to the T1 excited state. Over here, this is also a spin forbidden process. So I'm a little surprised about this number. We need to kind of double check this number because this is a spin forbidden process. So I think it's going to take longer than that. Those are just the acronyms. ISC, intersystem crossing, IC, internal conversion, VR, vibrational relaxation, S singlet, T triplet, S zero ground state, S1 first excited state, T1 triplet first excited state.